Bem, bom dia a todos e a todas. É um prazer muito grande hoje poder apresentar o professor Shukla, Jagadish Shukla, originalmente da Índia e cidadão americano também. Trabalhou na NASA, criou um grupo mundialmente conhecido como COLA, que é o Centro de Interação, de Estudos de Interação entre o Oceano e a Atmosfera, na Universidade de Maryland. Posteriormente foi criada uma corporação com esse nome no estado de Maryland e recentemente, eu acho que no mês passado, esse grupo passou para a Universidade George Mason, em Virgínia, que é próximo, né? E lá, grande parte dos professores desse centro se tornaram professores titulares, etc., da Universidade George Mason. Shukla é um líder mundial nessa área de clima. Em 1982, quando estava na NASA, ele propôs que variações lentas na superfície das águas dos oceanos, em termos de temperatura, poderia conduzir o que iria acontecer no clima nos meses seguintes. Depois foi em 82, etc., escreveu alguns papers sobre isso e deu fundamentos para essa técnica que nós conhecemos hoje como previsão sazonal de clima. Na época, obviamente, duvidavam um bocado dessa história, hoje é muito claro isso. E a nível internacional, isso serviu de base para o projeto chamado TOGA, que é um projeto de interação entre os oceanos mundial, principalmente os oceanos tropicais e a atmosfera global. Então, já há alguns anos, desde 82, o professor Shukla tem liderado isso. Fez seu doutorado no Instituto de Tecnologia de Massachusetts, com o Papa da Meteorologia na época, que era o professor Jim Charlie, que fez a primeira previsão numérica de tempo em 1950 em Princeton, usando aquele computador ENIAC-4. Então ele tem aí o seu DNA, toda uma história de meteorologia moderna que se foi feito, e obviamente continuou fazendo essa pesquisa, montou o seu centro e tem sido extremamente ativo. Trabalhou bastante na questão do PCC, nesses últimos relatórios, na parte de modelagem, e tem sido um líder mundial na área de modelagem matemática, usando supercomputadores, usando modelos globais, esse tipo. Ele está acompanhado da esposa dele, a Shukla. Eles conheceram na época que era estudantes lá no MIT, ainda a origem é grega, Universidade Americana também. E agradeço muito a presença de todos vocês aqui. Nós temos aqui o diretor do Escritório da FAO do Brasil, muito obrigado por vir. E tem uma pleia de colegas aqui. Eu vejo o Martini, que é da Agência Espacial Brasileira, Zete, colegas da Universidade Nacional de Brasília, e o pessoal do próprio Instituto aqui. Eu vou citar todos, porque essa é uma lista excepcional. Bem, isso feito, para não tomar mais tempo da palestra em si, dando mais uma vez a boa-vinda para ele, vou passar a palavra para ele e aí começa a sua palestra. So that was good English.
Thank you for giving me some time.
You want to say something before you start?
Well, I really just want to say that it's such a pleasure to be here. Of course, it has been such a pleasure to come to Brazil every time I have come, and I've come several times. And because I was very fortunate to make friends with Antonio Moura 42 years ago. 71, we were students at MIT, and we have remained not only good friends, but very good professional colleagues. It was very lucky that when my professor Charney, I heard the name, Charney, Professor Charney and I were trying to work on this idea that the boundary conditions affect climate. We were very lucky because Dr. Moura visited us in Washington, and then we actually learned that this idea, actually, thanks to his insight, works very well for Northeast Brazil. Actually, so he became a very good supporter of this sort of general idea that the boundary conditions, the SST. So it has been continued collaboration with many years. So I'm very happy to be here. So You can hear me, right? So before I go and start going over the PowerPoints and talk about the details, which I'll try to speak over, let me just give you two most important themes of my lecture. Two themes. One is that, there you go. Okay. One is that, we are interested in weather prediction, we're interested in the seasonal prediction, the droughts, we're interested in decadal prediction, what will happen over the next 10 years, and we're interested in the climate change, what will happen in 100 years. And normally, these four problems are studied by different groups, different people. I think one of the ideas that we have been working on, and now it is accepted, I think, very well, that this is a seamless problem. The word is seamless. In other words, weather, seasonal, decadal, climate change, we have to attack this problem in a seamless way. You cannot just do weather prediction and not worry about the climate. You cannot do just seasonal prediction, not worry about decade. You cannot do decadal prediction, you cannot worry about climate change. So that's basically one theme, and I'd like to show you. And the second theme of my lecture is that what is the status of predictability now? Where do we stand? What have we done? And what is the next big challenge? And of course, I have, and all colleagues, we have one hypothesis, and I'll try to describe that hypothesis. And again, I'll tell you just very briefly what the hypothesis is. The hypothesis is very simple. Of course, we need a lot of data. Without data, we cannot initialize the model. But almost the entire limit now, given such an amount of data, the way we are progressing, depends upon the fidelity of models. So the key word is fidelity determines predictability. Okay? So therefore, the challenge is to improve the fidelity. So these are the two themes of my talk. So if you keep that in mind, then you can skip over a lot of slides, and I'll skip over myself because of the time. So let's see. I think that I just wanted to show you a cartoon. Well, not a cartoon, but it's a very, I learned myself while preparing this lecture. Sad thing about that you must have heard about the famine, one of the biggest famines in India, and the number of people who died in 1876-77. And of course, India was in British rule, so the British ruler kept sending the food from India back to England, but in the middle of all this. But look at what happened in 1876-77. What was the big climate event? 1876-77, El Nino. 1876-77 was the biggest El Nino ever observed. And in fact, the only one that was observed was in 1882. So I wanted to show that as a motivation, that what we are going to show is in the end, that it is the boundary conditions of Pacific, Atlantic, Indian Ocean, which are going to help us with the seasonal prediction. Now, why seasonal prediction and climate change are so linked? Climate change, say 100 years from now, the adaptation to society has to be done at seasonal scale. Every season, every year, society has to know what is going to happen in the new climate, what will happen in the next. So unless we improve our seasonal prediction, we cannot actually manage the society, even if we can tell today what will happen in 100 years. And how does the society feel climate change? Not by some global mean temperature, 1 degree or 2 degrees. It feels by the extreme events. The probability of extreme events goes high. So therefore, we have to have very high resolution global models who can actually capture the extreme events, and then you find their change in the probability in the new climate. So you can see the idea of why the weather, season, climate, we really need to deal that as a problem. So there are many items in this talk, and I actually, I can give a course on this actually, but so I'm just really going to attempt to capture, because I haven't been here well, this is my first time. So I thought I'll capture most of the things that we have been doing. So I think I'll basically address the 3 questions, okay? Because I know many of you are interested in the weather prediction. What do we do then? What happens when you go from weather prediction to the seasonal prediction? Weather prediction is well defined. It was defined 100 years ago by real conditions. We are really trying to improve the recent conditions, and we are trying to improve the model. But once we go from weather prediction to the seasonal prediction, in addition to weather prediction, everything that was here, plus we must have very good knowledge of the boundary. And in addition to the boundary prediction, we must have our computers. It's very important because weather prediction you can have deterministic, but as you go to the seasonal prediction, it has to be probabilistic. And therefore, in order to do a probabilistic, you must have a large number of ensembles. In order to have a large number of ensembles, highly useful, you must have a very powerful computer. So every country I go to, USA, I didn't have time last night when we met Dr. Rao, but that's the normal request. We always want bigger computers because that's the way we can advance. I was very happy to see such a powerful computer in the last few years. We need that. We need more. I think you just have to keep telling your minister always, more computers. I think that. And then when you go to climate change, in addition to all that, you also have to take the gases. What is the change in gases? And then we have to put the uncertainty. Our biggest problem in prediction of the 100 years is not just the models, not just data, but what scenario do we take? What scenario society will take? How much we are going to consume? Which is another. And that's why we make scenario. So these are actually the 3 items that we wanted to. The weather prediction, I will not spend too much time. Everybody here is an expert. And Jody and I are both students of Dr. Lorraine, so who showed that there is a limit. So we know there is a limit, but we are trying to push that limit constantly. That's what we are trying to do. Because I don't believe we have reached that limit myself. And I think that this is the skill score, say from 80 to 10, let's say. This is the success story of our field, all right? This is the success story of our meteorology. There are very few areas where you will see, the only curves like that you see, just keep going up and up, is population, for example. But this is a scientific breakthrough that was made by our gurus 50 years ago, 60 years ago. And we constantly are improving skill at some large scale. We still have a challenge in the small scale, predicting convection, whether you have a small microburst or whether you have a big rainfall event here or there, we don't know. But we do have, we are making very systematic progress, and we understand that, what it is. And that's what I say. I'm not going to spend too much time. By the way, we know already that there is a very strong annual cycle within the weather prediction. I'm sure you must have the same experience. If you define a skill in any way, it is a very strong annual cycle. And we understand that very well because it has to do, again, with a very simple theory that how fast the error grows. So if the error grows fast, your limit is less. But if the error saturates fast, then also your limit is less. So if these 2 quantities determine the limit of predictability of weather. The rate at which the error grows and the value it saturates. And this is what we have understood. And we cannot control saturation value. That's weather. That depends upon the nature. The only thing we can control is how fast the error grows in the beginning. Once the error started growing, you cannot control either. There's a particular instability, there's a easterly wave, there's a cyclone. So this is actually the region we are going on that. And so you can see you can understand the basic concept that here is time and here is days. That during the summer, the error saturates very fast. That's why our limit is less. You can replace the summer by tropics. And this by mid-latitude, extended. So that's why we can have a skill in weather prediction in mid-latitude, a few days, longer than in tropics, because of the situation that we had broken. But that, I think that I'm going to show you that, look what has actually happened from 82 to 2002. This is the doubling time. How fast the error grows. I was telling you the error grows fast. 1.9 days, the error doubles. By the way, people are all told whether limit or whether predictability is 2 weeks. Where that came from? It came from these two numbers, doubling time and the saturation rate. So the reason we say 2 weeks or 10 days is because if the doubling time is 2 days, then suppose your initial error is quarter of a degree, the smallest you can have. In 2 days it will become half a degree. 4 days it will become 1 degree. 8 days it will become 2 degrees. That's where this limit came when we say 10 days, 2 weeks is the limit of the limit. But here is the very interesting observation. 82, the doubling time was about 2 days. It took many years and many studies, Lorraine, Charney, and a lot of studies we did to find out that number. Lorraine did it just in the back of the envelope, and all the models said yes, he did it right. That's the genius of Lorraine. 2 days is the doubling time. Look at now, the doubling time has come down from 2 days to 1.2 days. What does that mean? That means that the error is growing faster. So that will say that your job of making weather prediction is getting different. Why? Because once you have a model with very high resolution, you are resolving scales which are small, and their error grows faster. So therefore it is, on the other hand, here is the thing that the scale is going up. This is correlation 0.65 to 0.8. This is what I showed you, the scale is going up. So why it is going up? The scale is going up although the error is growing faster, all because of our initial error. Now the initial error has come down to half, from 40 meters to 8. So you see, that is why it is so important that we have the right initialization. We have a lot of data to be able to initialize the initial information. We're still struggling. We get a lot of data, but we don't know how to initialize them all. There's just such, we haven't advanced. So it's a challenge, global challenge, how to be able to define the initial information. So I think that weather prediction is still, we are on the path now to improve it. And the reason I wanted to cover that in the first part of the talk. And here is my example to show that why it is so important to have a good model. Take the model of today and go back and make forecasts for the last 20, 30 years. And your skill is very high. So I showed you in the beginning, your skill is going up. But that's because 30 years ago we were using 30-year-old model. Today, I can take the model and go back 30 years. And we can give. So I think that this has made a very clear demonstration that we do need to continuously improve the initial conditions and models, which has been a challenge. So now I'll jump over from the weather prediction to the season prediction. So what do we do? In weather prediction, it was very easy for me to explain why there is a limit, how do we improve by using seasonal prediction. Because this error keeps growing and saturating in 10 days, 15 days. So how do we predict seasonal prediction? This is where our work for the last 30 years has been mainly to show that the seasonal prediction is, I'll show you the diagram. Okay. So in the seasonal prediction, you do the weather prediction, plus now we must look into not the atmosphere, but also the ocean and land. We must take it. We must take also the gases, incidentally. You will be surprised that it is big, and you must take the soil moisture, vegetation. You must take all the boundary pieces to be able to do that. And I think that's to and I think that this has been a challenge. It has been a challenge challenge for, this has been a challenge to be able to do initialization for seasonal prediction. So you can imagine, weather prediction centers, there are 50 centers in the world, right? They're all doing every day weather prediction. So in the last 30 years, we have made at least 5,000 forecasts. Okay? The seasonal prediction is done only by a very small number of centers. And you predict only each season, let's say even if you go every month. So we have only 5,000. We have much less samples. So we are still in that stage of trying to improve the. And I'm going to skip the mathematics. Just believe me that we have shown that theoretically it is possible to predict seasonal activities. Because you remember in the beginning, I said weather cannot be predicted beyond 10 days. So now I'm saying, but seasonal averages can be predicted. So this is where came our basic theories we call predictability in the midst of chaos. So we are dealing with a system which is chaotic, and we still can show the predictability. And all the work that we have done in the last 20, 30 years is in that class. Indian Ocean, boundary condition affecting monsoon. Pacific El Nino affecting droughts all over the world. Work in Brazil with Antonio. Not SST in the Atlantic affecting northeast drought. Okay? Sea ice anomalies affecting polar climate. Like that, there has been a collection of thousands of papers in the last 20 years to make this point that yes, the boundary conditions are important. Then came the big breakthrough that can we predict the boundary conditions? And that's where the scientists from Colombia that Antonio was leading this institute, Kane and India, showed that yes, we can predict the boundary conditions. So you see, that gave us the basis to start predicting the boundary conditions and the seasonal means. So I think that's sort of, and I'm going to actually, again, let me see if I can go. Just, I will skip 10 slides or so, because all I'm going to do in those 10 slides is prove this concept, okay? So again, I'll say, just believe me, that this has been a big result that we have found, that the fidelity of the models determines predictability. That's sort of the So I think I'm going to then go back. So now, why I chose monsoon in my title of the talk. That talk would have been given with Northeast Brazil as an example. And I could have collected all the information about Northeast Brazil. But my friend didn't give me enough notice. So, about this. So I had it. So the ideas that I have given you are universal. Vitality determines predictability. That's universal idea. Limit of weather predictability. That's universal. There's nothing. Seasonal predictability, out of fact, that's universal. But just giving idea is one thing. I thought I'll give some example. And that's why I have used the monsoon as the example. And I'll show you one example of the monsoon. And of course, I have to say, monsoon is very tricky. I am from India. So I am very interested in Indian monsoon. Antonio was interested in Northeast Brazil drought predictions. But I had a very bad luck. For 25 years, the worst prediction in all the models that I worked at my center gave worst prediction of monsoon. And then many people actually in the world started saying that, you know, there's something wrong with the hypothesis that Johnny and I have given that is predicted. And the reason I chose the monsoon today for my talk, to tell you that I'm very happy to say that only last year we found out, after 50 years of climate modeling, for the first time now, models have become good enough to predict monsoon. So we never had that skillful prediction. We had very skillful prediction for El Nino for many years now, 10, 15 years, 20 years. We had skillful predictions for north of Brazil because the monsoon we did never have. And this picture tells you why. That's why I showed you. This tells you why. I mean, look how complex is the structure of the rainfall. And India government wants us to predict just the average over here. Okay? And sometimes this can move this way, this can move this way, and it will completely change the focus for the season. So it has been very difficult. But I think finally we have got skillful monsoon prediction. And then I'll tell you why. So it is, of course, it's very simple. And so I'm going to skip you. Anyway, I got this line from the. Is there any physicists in the room here? Because you'll know. Physicists can get away with this is from Physics Today, and I was so surprised when I saw this sentence in the Physics Today. These are very top physicists who are doing the modeling of the galaxies, and the guy said, "We really have very bad models, and now we can say we're making progress." So that kind of confidence they had, we never had that confidence 30 years ago, but we do now. In fact, now when we go to a meeting, we are very comfortable with telling our model is very bad. Because we can say that because it's doing so many other good things. And now we want to improve that model. So I think that this is a theme that I will come to at the end of my lecture. If you are a climate modeler, you wake up in the morning and you ask, what is the goal in your life? What do you want to do? Well, it has to be build the most perfect model. Then you will immediately ask, well, what is a perfect model? Well, a perfect model is the one which can capture the past line. Just the past line. You can never say anything about the future. So this is what the challenge is. That we must build the models which can capture all the fluctuations of monsoon, all the fluctuations of El Nino. Not the day by day, not month by month, not season by season, but the statistics. So number of droughts you had, you should have the models in that. And so this is what we are told, and in the end of the lecture, I'll come up with a proposal. Okay, how do we do it? So I think that maybe I can give you a quick overview that how are we going to realize this dream of building a model and improve weather prediction, seasonal prediction, and the climate change, all at the same time. So please remember that all the results I showed you of weather prediction, the 30, 40 years progress that we are making, they are all still based on potential verticity dynamics. What do I mean by potential verticity dynamics? The basic resolution of the model has been of the order of 100 kilometers all these days. Now they are beginning to have 10 to 30 kilometers. But still, we are predicting synoptic scale. That's what I mean. That's all we predict. Synoptic scale. So for the last 50 years, our entire work has been prediction of synoptic scale. Our challenge in the future is to be able to predict cloud systems and event systems. And that is where the challenge is. That because then only we'll be able to get organized conception, organized systems that we have. So this is where what I meant is that you see why I gave the original theme. We were dealing with a seamless problem. We really need to seamlessly address convection, weather prediction, synoptic scale, MJO, El Nino, and so I think that this is something that is really what is the challenge for, I'm not saying just for Brazil or just for India, just for the global just for the global weather climate community. This is what. So I think that the purpose of the next 10 slides was to show you that not only the ocean is important, but also the land is important. This is, by the way, the name of our center that Antonio mentioned is COLA, Center for Ocean, Land, Atmosphere. And I'll tell you a very simple story. We learned for the first time that the amount of evaporation from the land is 60% of the amount of precipitation of the land. So the evaporation from the land, evaporation from the trees, evaporation from the vegetation, from the Amazon rainforest is very large. And therefore, this is something well known in Brazil because Amazon does a lot of recycling of this evaporation. But globally, it was not appreciated. So the land is very important for seasonal prediction. And we are now trying to find out how to improve our seasonal prediction using land information. And conceptually, it makes sense. You can have a very hot spring and a dry spring. So when the summer comes, it will have very low warm temperature. And therefore, it should be able to affect circulation. In the winter, you can have a very large snow cover. And when the spring comes, all the energy will go to melt the snow, not heat the ground. So you can understand it. But in models, it has not been easy to do that. Conceptually, it looks like it should work out, but it hasn't been easy. So I think I'm going to just click on that and show you that we have got many, many examples. And I'll come back to the incidentally, we are making some progress in predicting the whole rainfall structure. This was the purpose of this. Now, let me tell you the challenge. What is the problem? That's why nature keeps us honest, right? We come and give a theory about predictability, very large. We have made a breakthrough now, science is advanced, we can predict seasonal mean. Comes 1997, one of the biggest El Niños, right? One of the biggest El Niños. India thinks it's going to be a big drought. We're getting phone calls from the Planning Commission, from the Prime Minister's office. Everybody's so worried that because you remember I showed you the El Niño in the beginning of the class, in the beginning of my lecture, 1876, huge drought. 1997, El Niño was so big. We were very worried and we predicted. What happens? India, no drought. Okay. On the other hand, you see, it is very, very little. Whereas the models are predicting huge drought. Look at the model. So now another research topic for the next 10 years, another 10 PhDs to find out what happened. Why such a big El Niño? And I'll just again skip many slides and give you the answer that we have come up with. And the answer is that not only the Pacific El Niño that is important for the monsoon, but the Indian Ocean SST is very important. So you can see why we're now going not just one ocean, but the global ocean is important to be able to do that. So I think that we have this is a PhD thesis of one of our students, and you can get the picture here. This is the Pacific heating, Pacific cooling, and this is the Indian Ocean heating. Take this out, and then your monsoon prediction is very bad. That's what happens. Put that in, and then we got reasonable monsoon prediction. So it's just to prove that, okay, we have to look at Atlantic for one region, Pacific for another, Indian Ocean for the other. Okay. So I think that, and as I say, this is the whole PhD thesis, so I'm just going to skip that and come back to the prediction of the Indian monsoon. So this is where I told you that, look at 1877. This is what I was showing. Look at the whole India was drought. Whole India was drought. Look at El Niño. Biggest El Niño. This is what I showed. Okay? In 1918, same thing. Big drought. Big drought. It was one of the, years. Big drought, but no big El Nino. 1899, big El Nino. So we are trying to predict the monsoon, and here's the challenge. We want to predict June, July, August. That's what the monsoon season is. But there's a big correlation between El Nino and monsoon. But in order to predict June, you have to give the forecast. Government wants the forecast in March. What will happen in June, July, August? There's no relationship. And that is why Walker actually, most of his forecasts didn't have much skill. But that's because of the. So now we do have this skill. Again, the same figure. See, look at the correlation is very high, 0.6 in June, July, but very little before that. So this is a problem. You want to predict in summer. Correlation is very strong between El Nino and monsoon. But you don't know in March what is going to happen in June, July. Right? So that's where the couple model came. And now we are able to do. So I told you that in 50 years, we are able to do the prediction. We are able to do it because in March, we are able to predict what will happen. Not the rainfall is still hard, but to El Nino. And then that produces the relationship. This is basically where the prediction came, and I'll show you. So, India has been issuing forecasts for 100 years, every year, right? More than 100 years, 125. What is the skill of the Indian seasonal forecast? Of course, I work very closely with India, so I can say zero. The skill of seasonal forecast is zero. Because you have to define, you see, some years you can get correct, some years you can get wrong. That doesn't mean you have a skill. If you just randomly toss something, you'll get sometime right, sometime wrong. So you have to do a very systematic analysis and find what is the skill. It's zero. There's no. And we repeated it to show that. And you see, this is what it is. The correlation is very small. This is why what India uses either January, February, all the way up to May. But look at the models now. We have got 6 models in the world, and this is a multi-model mean. Very high score. So this is what I was trying to tell you is that this is after 50 years. It is a pleasure to see that finally the model fidelity is getting such that we can get actually. And I can just explain to you that, which I said before. The reason that skill has come is because look at the skill of the El Nino. So this is the point I said. So we are able to predict monsoon not because our monsoons models can predict the rainfall 6 months in advance, but because we are able to predict El Nino 6 months in advance, and then use that El Nino monsoon relationship, which is not perfect, but you can use that, which is much better than any other statistics that we have had. That's where the prediction has come. So I'm going to actually come back to the. Okay, I still have 5 minutes, right? 5 minutes, 10 minutes. So I tell you what I'm going to do. I'm going to come back to summary, but before I do that, I wanted to take 5 minutes, 3 to 4 minutes, to tell you the monsoon is a changing climate. What is happening in the climate? And look, so these are the, well, you can read that, so don't worry. This is the average of more than 23 models. Anyway, tomorrow, I think IPCC, tonight, is going to release the results, and you will probably see, it will be all over in the news on this. But the data was available before, so we could collect data and do some research. And so look at that, the change. Of course, this is the scenario where a lot of CO2 is being released. This is that scenario. And this is the difference between 2071 to 2099. So take the 30 years at the end of the century. Okay? and take the current climate and take the difference. And this is the temperature, which is very well known. Of course, we know that the temperatures go up by 3 degrees, 4 degrees. This is what all the models are showing. But look at the rainfall. There is a very systematic pattern of the increasing rain in the coming And now, one of the challenges is to be able to explain, because if you look at the SSTs, see SSTs, the warming of the SST is not, it's there, it's almost like an El Nino. You can see that. But look at this is a global pattern which seems to be very robust in there. And if you look at over India, because this was very warm, both rainfall increase and the temperature increase. The temperatures are about 4 or 5 degrees on the, and if you look at, so we have 23 models. So it's very consistent between the models. Some models are more, some models are less, but it's very consistent. So even if you take a multi-model, you get an average. Okay, so let me just go back to the my summary, because this was, I wanted to come to the climate change. I didn't know whether I'll have to. Okay. So I think that two summaries I just wanted to tell you that it is for the monsoon. What do we find is that there is the skill, but that skill is still very much dependent upon our ability to predict sea surface temperature. But it's just not the sea surface temperature. The sea surface temperature has to produce heating. And that's the problem. So the heating simulations in Pacific and Indian Ocean both have to get better. Same thing with the Northeast Brazil drop. All the models, you can predict the sea surface temperature, but if you predict them correctly, and if you cannot predict the heating that is associated, it will not change the circulation. That's a simple point. And the main result, of course, we found is that we do have there is a very sensitive dependence on this. So look at the bar. What I have, all like NWP. See what I mean? What I'm saying is that what we did for numerical temperature in the last 50 years, we need to do that now for climate change in a way system. So the proposal that many of my colleagues and us, we have been discussing all over the world, but not succeeding, of course, failed, I should say. We're saying that, so you all know about CERN, right, at Switzerland. CERN is a very powerful accelerator that physicists collected funds from all over the world and created CERN. And finally, they had a success last year. They got the Higgs boson, right? I mean, they got the Higgs. So we are trying to propose, what about climate CERN? You see what I mean? Climate CERN. Climate CERN means, okay, we have many countries in the world, 10, 15, 20, including Brazil. They have got many, many powerful computers. Why don't we create one global, one or two, maybe one is not enough, you have to have more than one, maybe 2 or 3, rather than 30. Very, very powerful computers, a very large number of people. And see if these challenges that we have been going to do, because this is a sentence that I am quite maintaining this, that right now we are not limited by the limit of predictability. See, this is the thing that I wanted to know, because there are the reason we are not predicting is not because there is no predictability. There is no theoretical limit. There is no barrier. But we are limited because we do not have the right kind of observations, the right kind of very sophisticated models, and very large number of scientific staff which can address convection, radiation, boundary layer, ocean, land, and so on. This was really the the grand statement that comes out of this kind of talk that I try to give. Okay, thank you very much. Thank you.
Ok, muito obrigado pela excelente palestra. Now you can have some questions. I think in climate we are concerned with the predictability, but we don't have a CERN. Concerned.
He's good at playing with words.
Ok. Bem, a gente agradece a brilhante palestra dele, também na linha de frente, em termos de pesquisa. A limitação, o limite de previsibilidade dele, que ele conseguiu prever que a palestra seria em português e tal, então fez em inglês mesmo. Né?
You can ask questions and I can translate.
Yeah. So I say that your limitation that you don't speak Portuguese, that's why it's a limit of predictability.
Oh,
Bem, está aberto então para perguntas e comentários, etc. Pode ser em chinês também.
yeah, yes. That person. Yeah. No? Oh, no, you stretch.
Professor Jagadish, Shukla, é uma pergunta provocativa a respeito da importância e da utilidade das previsões, seja de monções, seja de secas, como as que ocorrem aqui em vários países da América Latina. É que as previsões que funcionam são sempre previsões de curto prazo. Eu fico quase com a conclusão que o senhor colocou aí sobre a dificuldade de prever as monções. Questão aí, né? Falta de dados insuficientes, modelos inadequados e falta de uma capacidade científica bem treinada. Né? Então, se as previsões são efetivas, são sempre de curto prazo, quando se está diante, você vai conseguir ou para você? Você quer. Deixa eu repetir.
Sou nem especialista, mas posso tentar ajudar.
Deixa eu repetir.
Até eu peguei.
Pegou? Então, segura aí. Então, se as previsões mais eficazes são de curto prazo, como é que nós vamos torná-las eficazes em relação a países ou áreas onde que sejam densamente povoadas, como a Índia, como o Bangladesh, como o Paquistão, como os países da Ásia, né, em geral. Eu tenho uma previsão que daqui a um mês vem uma tsunami, o que é que eu vou fazer com aquele mundão de gente? Esta é a lógica da indagação.
Good question.
Well, it was a lecture, not a lecture. It's going to be translated by an English professor.
Oh, okay.
Professor, it is a professor.
Okay.
All right. He initiated by saying that it's a kind of a provocation. He says that given that the forecasts are very often based, the efficient forecasts are often based on a short-term result. How can we operate in deeply populated areas like southeastern Brazil or regions of India? So he says that there is a certain limit on that, and would like you to explain a little further.
Okay. First of all, yeah, it's not a. No, okay. No, it is not a provocation. It's a good, it's a very good question. Much of my lecture was discussing predictability of synoptic scale. The question of predictability of very small scale, the one that you using models which have extremely high resolution, is still an open question. It's a very open question. The problem is that we cannot address the problem without putting a boundary. We put a boundary because we have to make a regional model, very small regional model. And you cannot say that what part of degradation of your forecast is because we don't have good predictability, or is because we are putting an artificial boundary. The wind doesn't care about the boundary. You know, there is a, so one of the ideas of this very high resolution model is that you don't have to put a boundary. But still, it's a very good question that we must evaluate that if we do have very, very high resolution model, if we're talking about, let's say we're talking about 100 meter, 500 meter resolution, and have individual hills, every building, every little, whether, and then what is the scale? So there becomes my personal philosophy. I'm an optimist. And I feel that it's a problem that has potential predictability. We cannot say it is not predictable. We just need that effort to be able to test with this new kind of model. I think, and it will be done, I'm sure.
But I might make a comment on that. As a head of a Met service, I have not only to engage the researchers
Yes.
in the field, but to be practical, to serve society, right? So I think that the problem here always remains. 10 years from now, you're going to get better knowledge than today. 20 years from now, better. As we have now, because humans have memory, we're able to remember things, accumulate knowledge. So the question should be reversed. What's the best use I can make of current knowledge? And prepare society, an infrastructure to deal with those changes in several time scales, in several spatial scales. So once you develop a nice infrastructure, like in the Northeast Brazil, instead of trucking water, you have reservoir, you have other things to do things, you're better off to do that. Okay? So if you compare the case of Northeast Brazil, 1800 something, there was a major drought. Huge, millions of people died in Ceará. Why in the recent last year, this year drought? Nobody died because of the drought. Because a lot of infrastructure, communication, we were able to bring food. 1800, you didn't have way to communicate. You're going to take a horse, come to São Paulo to tell people that you're dying of hunger there. People are actually. So the infrastructure, those things that you have to set, like policymakers, understanding that weather, climate changes in several time scales, etc., and establishing proper infrastructure, you better do it. And Shukla addressed this because he mentioned that as you go to 10 years from now, you have to go to a season. As you go for 100 years from now, you have to go to the next year. So we have to encounter those things, and we're better off to adapt to the shorter variation that has big swing, big amplitude from winter to summer, from a drought to a very wet year. So those things, I think, become, from a social scientist perspective, from a government perspective, very important to do. Okay, he's going to answer now. He was just challenging you as well.
Yeah. No, this is, I forgot to say something very important. Two things. One is the very fact you are asking questions like this, that shows the progress. Because see, I'm saying we can predict synoptic scale, what will happen over entire Europe, and you're saying, no, but I want to know about the city. So that's a sign of progress. But the point I really did not mention carefully, and this is a very important point that Antonio's comment reminded me, because after all, he has to face the music. And I do that in India all the time, but I forgot to mention, we as a scientist have a responsibility to not give false hope of what is predictable, what is not predictable. Okay? That's very important. We must be able to tell the policymakers that this is the limit of predictability. See, the purpose of my talk was to tell you how do we find that limit of predictability? What do we do? How do we go about it? But we must tell the policymakers, this is the limit of predictability. I tell you what is happening in India. The Minister of Science, because the weather comes under the Minister of Science, is now saying, oh, I want prediction for every district. 2 weeks prediction for every district. And we are trying to tell him that it is not possible to predict every district 2 weeks in advance. We can predict 2 weeks in advance on large scale feature. So that's a very good point. I think we need to be careful about what do we promise to society, knowing all the limitations we have. Yeah. That's a very good point. We need that promise.
Okay. Martini. I like Martini a lot. It's right. Wet as well. Wet. His name is Martini. Not a drink.
So, I am a geologist, and you know, for geological times, they run very, very, not that fast as climate change, but some guys are saying that we are going to a new geological era, maybe. They call it Anthropocene. I would like to know your opinion about this. Do you agree? What the facts and your opinion?
Martinez was a researcher from UP in Los Angeles geologist. Now he is the chief of staff of the Brazilian Space Agency here in Brazil.
First of all, I'm very happy to hear this question because I was a geology student in college myself.
Have a first PhD?
Yeah, right. I had my first PhD from geophysics, but then I got a job in meteorology, so I did meteorology. That word was coined by Paul Crutzen. Paul Crutzen is one of the geochemists, and to me, as a geology student, I'm not very excited about that because it was done more for political reasons to be able to show that we are going to have a huge change. The reason I don't like it as a geologist is because all the other similar terms in geological history witnessed huge changes, which are geological, and so, given that very frank opinion, all he's trying to do is say that this is the first time that a change in the climate is going to be completely because of the human activities. It is we're going to get the human activities are going to be responsible for a transformation of the climate. So therefore, Anthropocene, because anthropogenic forcing is causing the change. So in some way, it was a very grand way of bringing to the point to that we are fundamentally changing which many people don't completely agree. They feel that, there's a lot of debate, but that was the idea.
Professor Shukla, I want to thank you very much in the name of our colleagues from Inmet for an excellent class, actually. And I'd like to take the opportunity to make a small question on a very specific topic within this whole picture you so well showed us. I'd like, if possible, to listen a few words concerning seasonal forecasts and statistical models. Most of what you addressed has to do with models, but could you say something about how the whole statistical model can still play in this whole picture?
So one of the PowerPoints I skipped was about the statistical model. My colleague, Tim Del Sol, his name is Tim Del Sol, and I have written 5 papers in the last 5 years on statistical prediction. These are not very kind papers. These papers are not very, because Del Sol is a very great statistician, and he went one after the other and showed that all the statistical forecasts that India was making, he can make better forecasts by using random numbers as predictors. Then he went to Bill Gray study, and he showed the same thing, that Bill Gray makes predictions, and they can be reproduced by and then we found out the reason is because the way the statistical models choose predictors, they take 100 years of data and find correlation, and find this has very high correlation, then use that as a predictor. This is a fundamentally false method of choosing predictors because it produces artificial skill. So the 2 points we mentioned was that we get artificial skill and we do fishing. This is called fishing. You know, when you go and find correlation and find, it's called fishing. You are like fishing. But both are very objectionable techniques. And if you don't do that, our conclusion is that it is not possible for the 2 cases we have done, Indian monsoon, to make statistical forecasts which have any skill. So statistical forecast, that's what Walker was doing. So we published this in the last 5 years. So now I'll tell you the story. 6 months ago, there's a professor at Hawaii, Bin Wang, that you know. So he has sent us a paper, and he said, all these papers these people have written and say there's no skill. I have now a new statistical method which satisfies all the criteria and there is a skill. So anyway, we are studying that. So I should not be so strong about my views. But after the model result that I showed you, I have told the Indian Minister of Science in India, that they should stop statistical forecasting and work on many other countries like that. So, and then the Director General of Indian Meteorological Department said, no, we must stop, don't believe what Shukla said. So my point is that this is still going on as a debate. So I'm giving you my personal opinion. My personal opinion is I have a lot of respect for statistical methods. They are very, very useful. But right now, we have to find models which can beat the statistical methods. But still, there is need for some statistical protection for those areas where models are absolutely not doing it. And that was monsoon was the case in last.
Yeah, I think Lau leads a good group here, trying to push the envelope of some prediction. When you look at the South America in general, we have very good skill from January to May of the northeast Brazil up to 0.7, 0.8 correlation for the precipitation, because now we understand the force and the heating that we have to do with IPCC, and that goes back to 1980 with calculus to that. So the skill there is very good for producing global volumes. In the region of El Niño as well, Peru, northern Ecuador, etc., South America a little bit. The major part of Brazil, that was a challenge I put to them some 3-4 years ago. In the central part of Brazil, where we produce most of the grain, and we are under the Ministry of Agriculture. What can we do about it? Is there a memory? Because once you're locked into some season, it doesn't change the next day. So it takes some time of listening to move on to the next kind of thing. So how far can we look at the data and push it what, a week, a month, 2 months ahead, and that seasonal dependence, and where you can have some skill that you can merge the stochastic model with the global model.
Oh, very,
We have
very
been
good.
successful in that.
Very, very good point. Oh, again, his comment reminds me that I didn't give you the one part. My lecture, there was statistical prediction in there also. So let me just distinguish now between statistical prediction where you are doing purely based on data.
Yeah.
What we are saying is that now if you take models and take the predicted values of the models, not the rainfall that you're predicting, but other properties, like the SST or the soil wetness, and then use statistics between the predicted predictors. You see what I'm saying? Rather than the observed predictors. This is what we are doing. In other words, already there is a skill in predicting some aspect of climate system. Use that in a statistical model. This is what we are doing.
Okay, Cardoso is from the water agency, he's a hydrologist. Always drinking water.
Well, first of all, I'd like to congratulate you for your presentation on behalf of the National Water Agency of Brazil. And, well, I have two questions, actually. The first one is, as a hydrologist, I'd like to know whether, I wonder if the measurement of river flow could add some value to forecast models, of seasonal forecast models. Because we usually, river flow is a consequence of weather. But to what extent seasonal forecast could be a consequence of, somehow, a consequence of river flow data? The model could be work better or not on it. And the second one is that you talk about insufficiency of data, inaccuracy of model, and lack of expert personnel. And what about inaccurate data, not reliable data? Thank you.
So the first part of the question is the river runoff, by the way, is a very important data set. And absolutely, it is very useful also to verify the model because it integrates a lot of weather events. And I think that if you write down the equations for the moisture budget, turns out that the runoff is exactly equal to the vertical integral of the moisture flux. So my point is that it's a very good data set. And we need more because it also helps us verify, which is a diagnostic point. Inaccuracy of the data. I think that it remains a problem, of course, and any inaccuracy in the data will then grow exponentially. That was one of the points that we have. I think that the accuracy in general, right now, our problem is coverage rather than inaccuracy. In other words, we just don't have no data. There are large areas where there is no data on this. So that has been our big challenge. I think technology is slowly improving, I'm sure. And when we look at the Brazilian 500 automatic weather stations, I have been looking at some of the stations also. India set up some, there's some question about the rainfall, but most of, the fluctuations. But there is a very good data set that we have. So I'm not an expert on technology. I just believe technologists are taking care of it.
We are concerned with the technology.
Yeah,
We are
yeah,
also
yeah.
concerned.
Dirceu Reis in University of Brasilia. I'm not a climate scientist or researcher, just a water resource engineer. My point is, you talked about a little about skill of the models. I'd like to have your opinion on focusing more on the value of this forecast for many types of decision, weather-based or climate-based decisions, for example, in agriculture or water resources or health systems, etc.
That's, I think Antonio made that point. That's a very important point. We do not have enough interaction between these model outputs, modeling groups, and applications sectors. There may be a lot of information in this model that is there. The models don't know how to massage it, how to bring it out, and so on. So no, I think that there is I concentrated on just on one element: better model, better science, and so on. You're absolutely right. There is another big area, the interaction between that and the application community. Yes.
Yeah.
Do you think it's possible, I'm not sure, maybe not, but that in order to decide how much effort you have to make in some kind of areas, because you're very focused on increasing the skill of these models, would it be possible you're making a mistake because you're not looking at how we're going to use this information, and maybe you should invest more money in people to figure out other aspects of the problem?
That's a kind of political question. It becomes political because the question is what is more important and how much we believe, the modeling community, we actually believe that there should be a lot more money should be spent on the kind of questions that you are asking. Because for one thing, it doesn't require a huge amount of money. You don't have to buy a supercomputer. You don't have to, you need a lot of people. So absolutely, we should spend. But I don't think it's a mistake. I'll tell you what we think is a mistake.
The conflicts that the question was not.
Yeah.
What question do you need to answer?
Yes.
My point is, well, maybe, because when we talk about school, talking about how better.
Right. No, I'll tell you the standard answers that my community gives to a question like that. Our standard answer is that, look, people are smart. The society is very smart. They will figure out what to use the information. You just produce better information. In other words, so long as you are producing better and accurate information, people are very smart, they will know how to use it. So therefore, there's no kind of, you shouldn't stop producing, because nobody will question that we need more accurate information. That's the but I'll tell you where we feel is a mistake. Although, this is a space agency, so I shouldn't probably say that, right? It's not a space agency.
It's a weather service.
It's a weather service, right? I mean, it used to be. So we always are complaining that the satellite costs $100 million, but they will not spend $10 million to process that data and produce that information to be able to make it for the model. You see what I'm saying? So that's where we think that think of one supercomputer as another small satellite. Then you get so much value out of the information that you take. We use less than 10% of the data right now, for example. So that's an argument, a debate we have. So my apology, there's somebody from the space.
Yeah,
Oh, okay.
no, he's taking right notes. He'll talk to Ralph tomorrow and Monday. Tomorrow. So we'll take a last question here, and then I'd like to address a little bit of that. There'll be two more. This one, and we have to end.
Okay, Professor Shukla, thank you very much for the lecture. I think it was very interesting and comprehensive. You mentioned that the success of numerical weather prediction was largely due to global effort. And you mentioned that you think that for climate you need another large effort on a global base. And you mentioned CERN. What CERN is an European center dealing with nuclear research, it was basically created and it's working with a very huge budget from advanced European countries. My question would be, how do you think that we could do that, the same thing for climate? That does not only involve European rich countries, but other countries as well.
Yes, yes. That's very
European, they used to be rich countries.
No, that's a very good point, and our proposal, and by the way, we have published this in the bulletin of our proposal was that the amount of money that is needed to do that is a small amount of money compared to the importance of the problem. Because we're dealing with the future of human society. We're dealing with how we manage with the climate change. And our proposal was three CERNs, okay? So think of it as the North America and South America as one unit, okay? Europe, Brazil, sort of Africa, and Asia, China, India, and so on. Because we have now a lot of other rich countries. And the CERN budget, and by the way, and our estimate was the budget is really just $1 billion. That's much less than what U.S. spends on Iraq.
It's like a stadium in Brazil.
Yeah. Okay.
Hi, my name is Sanderson with Atual. I work for the Ministry of Science and Technology. First of all, I'd like to congratulate you for your nice presentation. I have more a general question. I used to be a water engineer. I'd say now that I'm more a policymaker. And just from your presentation and from what you said, you've shown some slides on different images of El Nino and the effects that El Nino had in the past, in the late 80s, 1800s actually. In India and in the different parts of the world. Also at the same time, as Antonio said, we had a big drought in northeastern Brazil. And with these different models that science has been advancing, now what's the precision that one could say that we will have a certain period of drought or not? And so if we see throughout the years, the different years like that, we had different periods with droughts and more wet periods. Does it mean that the climate is not changing? Because people are talking, scientists, the whole society, even myself, we are talking about a lot of climate change. So what's the connection between the data that we have from the past, the new models, the advances, and climate change?
Okay, that's a very good question. Let me tell you, first of all, the first part of your question about water management. It is still a challenge. Because of the reasons somebody mentioned about the runoff question, I remember. Yeah, because of you see, still we have a problem in getting the integrated information good enough that we're still not using the modern predictions in our water management. And in fact, a lot of people in the US have shown that there is a challenge. So far as the drought prediction is concerned, they're actually the only thing we can predict with the climate change scenario is the probability of changes in the drought. So long as the actual droughts that are coming in a coming season is concerned, there we really have to go back and re-predict all the possible. This is what we're saying, that this is what is that effort. When I said that global effort is needed, what is that effort? That effort is go back 50 years and try to predict each of the droughts that you have. And find out what is the fidelity of your predictions and in how much in advance. So you will find some of them you could predict 30 days in advance, some of them you could predict a week in advance, some of them you couldn't predict at all because it was all total random. Yeah. You know, that is not done. That's what I said, that the seasonal prediction, drought prediction is in that class. Okay. because in some way, what you're asking is about harder than seasonal. You're predicting seasonal mean, that's easier. You want to predict during the season. Is it a 1 month long drought or 2 month long drought and so on? That exercise is just beginning to be done in the global community. And that needs to be done. That's what I meant by, just like the weather prediction, we have done thousands and thousands of cases. We have to do that. And I'm sure the Brazilian scientists will be doing that. Thank you.
Ok. Antes de terminar, eu gostaria de passar ao professor Shukla uma placa com a nossa apreciação pela palestra, pela visita que ele fez aqui ao Inmet. So I'll translate that to you. So I'd like to pass you a hand of thanks that describes how we admire your work and how Inmet feel honored to have you here today. So I'll pass it to you.
Oh, wow.
I want to take a picture before, so look at this. Very good. Okay, I'll read that. It's in my Brazilian English here. It reads, to Professor J. Shukla, in recognition of your worldwide leadership in climate science. Inmet, Brasilia, 27 September 2013. Okay.
Thank you. I knew I'd never.
So he got from the poll, from the president or prime minister, I don't know, from India. This is a small token, just to remember our friendship and the regional work.
Thank you all. I really enjoy it.
Okay, obrigado.